Today we're starting the third of the three topics we cover in this class, which is integration. And so the process that we went through with derivatives we'll also go through with integration. So you'll have a chapter that teaches you how to do integration, and then we'll do a chapter about applications of integration. Fun stuff. And then we'll be done. Then we just kick back and relax.
Yeah.
That's for pizza.
Okay.
Then we start reviewing for the AP test. Everybody gets a 5.
My shirt is black.
Then the party starts. What's the matter?
My shirt is black.
Wait, what are we doing after the order? Technically, we're supposed to.
I don't know what
Okay, so today you should be able to find a general solution. We're going to do this thing called a differential equations also. For those of you that continue on the math path next year, that rhymed, you'll end up taking an entire course where you do nothing but differential equations. It's cool. We'll also talk about something called an indefinite integral, which to you right now probably sounds like gobbledygook, but we'll get there eventually. We'll talk about some basic integration techniques, and we'll look for a partial solution to a differential equation. And again, this will make more sense as we move through here. We've got something called an antiderivative. So what do you figure an antiderivative is, Sid?
It's against the opposite derivative.
Beautiful. Opposite of a derivative, because it's the antiderivative.
So you leave it as it is.
I'm sorry?
You leave it as it is.
No,
you don't take the opposite.
do the opposite.
You do the opposite. You don't just leave it alone.
It's so much better. We should
It
do
would be a
that.
lot easier if you just...
Yeah, just do that.
I'm going to choose not to do the derivative, so therefore I don't have to worry about the antiderivative. We're good to go. Just write GTG on all your problems.
Okay.
All right, so it starts with a simple question. Suppose I have a function 3x squared. There is some function that I took the derivative of to get 3x squared. What is that function? X cubed, correct. Everybody see that? Started with x cubed, take the derivative of x cubed, you get 3x squared. That process of going backwards is what's called an antiderivative. Okay, so notice some notation now. I started with f. So what we've done already is we started with f, took the derivative to get f prime, took the derivative to get f double prime, took the derivative to get f triple prime, and kept going that way. If we go backwards, we go from lowercase f to uppercase f. Okay, so uppercase f means the function that I would take the derivative of to get the function I'm talking about. And we'll have some other notation that'll make this a little bit easier, but that's the gist of what we're going to do. And initially, I hope this isn't that difficult of a process. It's pretty straightforward, and it's very algorithmic. It's very similar to the derivatives, where you just do this, this, and this, and you get the antiderivative. Okay, does that make sense? Good. Again, terminology, antiderivative. And so, one thing we didn't consider, if we go back here, is there any other things that we could use for capital F of x? Give me.
Could it be like x cubed plus 1
Or,
plus 2
or,
plus infinity? Yeah.
well, I don't know, we put it, I mean, you kind of jumped the shark there, buddy. You were going strong, and then you had to go to infinity and screw everything up. Right. Okay, so his point is valid. If we had x cubed plus 1, if you take the derivative of that, you'd still get 3x squared. In other words, there's a whole bunch of possible solutions to that problem. And so we're going to talk about something called a family of derivatives. Okay, so there's x cubed plus 7 minus 12. I didn't throw an infinity in there. But again, this is a family of antiderivatives. There are actually an infinite number of antiderivatives for that function 3x squared. And so we need to come up with a way to represent that. Well, that's not too bad. We just throw in what's called a constant of, well, we'll get there. Let me click through it. Okay. In order to represent that there's some number there, and that number could be anything, we just use a capital C. That's called the constant of integration. So to just say that it's x squared, well, I changed functions here, so we're doing 2x and x squared. To just say that it's x squared doesn't make much sense, because it could be x squared plus 1, x squared plus 2, et cetera, and we represent that by a plus c. That is going to be a big problem for some of you until I eventually burn it into your brain that you have to have the plus C on there. Again, because we want to represent the family of antiderivatives. Eventually, we're going to switch and not deal with the families. We're going to get specific answers. That's coming up in a second. But in general, when you solve for the family, you just stick a plus C on the end of it. Now, the nice thing about antiderivatives is you can always check your answer. I start with a function, I take the antiderivative of it, I think that's the right value. If I'm not sure, I just take the derivative of my answer. If I end up back where I started, I'm good to go. Does that make sense? I'll take that as a yes. Question? Go ahead.
I might be like, yeah, this might the wrong thing to ask you right now, but like, how is this gonna work with like fractions and product rule and stuff? Yeah, I figured.
It's actually really easy.
Really?
I've got a couple flashy slides that'll answer your question.
Says the calc.
They're really important because they're flashy.
Flash.
Yeah, because we know how flashy means important. Okay, so let's start with something simple. I've got a function y prime, and it equals 2. Differential equation is another way of saying find the antiderivative. To find the equation that gave you that value. So for instance, if I start with y prime, let's just deal with the left side of the equation. If I take the antiderivative of y prime, where do I end up? Do you have another question, or are you going to answer my question?
I don't know if it's the right answer to your question. I was going to say 2x plus c.
Well, that's later. That's the right side. See, if you go like this, Greg,
On the left side.
the L is left. That's how I remember it.
I was before the-
That's easier than writing it on your shoes. So you hold that. Left side would be y, because the antiderivative of y prime is going backwards would be y. What would the right side of the equation be, Greg?
Oh, 2x plus c.
Well done. Good. 2x plus c. So that covers all the possible values or possible equations that we could take the derivative of and end up with just plain old 2. All right, so is this process starting to sink in a little bit?
Yeah.
Good. All right, now we need some notation. It's too much of a hassle to worry about capital letters and lowercase letters and all that other stuff, so we have a whole bunch of fancy notation here. So here's the symbol for integration. It's a little squiggly thing. Go ahead, practice it a couple times. It looks something like that. Okay. And this is where you can throw a little bit of artistic flair in when you're doing. So some people like to do dress it up a little bit. Yeah. Some people make it like a giant S. That's probably not so good. Okay. You want it to look like an integration symbol. Some people, like myself, get a little crazy on the end with the little flip up at the end. Okay, but that's a symbol for antiderivative. So if we take the antiderivative of f of x, we get capital F of x. What happens if I take the antiderivative of f prime? I get f of x. What if I take the antiderivative of f quadruple prime? F triple prime, right. So we're just reducing it by 1. Question mark.
So that symbol means antiderivative.
I can't hear you.
So that symbol means antiderivative.
You got it. Yeah. Yes, sir.
You take the antiderivative of f of x.
Capital F.
Capital F of x? Yes, you can. Are you asking me what the notation is? I have no idea.
We're going to do it.
No, probably not. Yeah. We're not real big on double integrals. No, an integral of an integral. Anything? Yeah.
Is an integral the same thing as an antiderivative?
Yeah. So we'll use those. Good question. We'll use those two terms interchangeably. In the antiderivative and the integral are interchangeable as far as what you're doing. Okay. I did want to point one thing out. Is that pesky little dx there? Okay, we'll talk about that in a second. So that stuff that you're taking the antiderivative of is called the integrand. that dx is called the variable of integration. It's really, really important. I'll explain why in a second. That's the antiderivative, the thing that you get when you take the antiderivative. And then we talked about c already being the constant of integration. And all of those parts are really important. So you'll recall when we were doing related rates, we had an expression that would say something like dx over dt. What did that notation mean? Dx over dt. Good. Derivative of x with respect to t. So what do you think that dx would do at the end of the antiderivative?
Say it again.
If dx dt meant take the derivative of x with respect to t, then what do you think that dx at the end of that thing does?
Take the derivative of that prime and respect to the antiderivative.
Let me ask you a simple question. What's my variable?
X.
X. That's all it does. It tells you what the variable is. So if we have an expression that has x's, y's, z's, q's, p's, whatever that's in there, the dx or the dq or the dp will tell you which of all those things is the variable. 90% of the time it's going to be a dx, but occasionally you'll get that little guy in there that screws things up. This process that we're going through is called, or the thing that we get is called an indefinite integral. Okay. Indefinite because we don't have one answer. We have a whole Gesundheit. We have a whole family of answers. It's also called an indefinite integral because we're getting an equation, not a value. Later on, not today, but in the next, after Thanksgiving, we'll talk about something called a definite integral, where you'll do this process and it'll just spit out a number, not an equation. Okay, but we're gonna walk before we run here. All right. Now we answer Jimmy's question. What happens when there's fractions and stuff in there? Or we get a weird function? You cry. There you go. That's one option. Let's talk about this first. So here we actually mentioned this, but I want to clarify a couple things. What happens when I take the antiderivative of f prime? I end up with f of x plus c. Okay. Any problems there? Since I took an antiderivative, well, first of all, I took the function f. I have the derivative of f. Then I took the antiderivative of f prime and ended up with f of x plus c, because there's a whole bunch of possible answers. Any issues there? All right. Things change, however, if I go out of order. If I do it the other way around, I could do this. Take the antiderivative of f, and I would get capital F of x. When I take the derivative of capital F of x, I get f. I go back to this. So notice, the antiderivative of f prime lands me at f. The derivative of the antiderivative of f of x ends me up at f of x. Why does this not have a c on it?
Because it's the derivative and it gets rid of all the constants.
Yeah. It has to do with the order that things happen. The top equation, we took an antiderivative, we took a derivative first, then ended with an antiderivative. So you have to have a plus c on the end of it. The bottom one, we took an antiderivative first, then took a derivative. Since the derivative was taken last, the constants would disappear. So no plus c. It's a minor point, but it does pop up every once in a while. And again, the simple thing to ask yourself is, what did I do last? Which we just answered. Sure. Finn?
Explain that again about the seed.
Let's talk about the top one. I did two things. I took a derivative and an antiderivative. Which one did I do second? Well, I did the antiderivative second. Or not even second, I did it last. So I took the derivative first, then did the antiderivative. Anytime you take an antiderivative, you got to stick a plus c on the end of it. That's why that's there. If I go down to this one, I took an antiderivative first, then took a derivative. Okay, so in other words, if I take the derivative of this, I would get capital F of x plus c, right? And then when I take the derivative of that, the derivative of capital F would be lowercase f of x. What's the derivative of c? 0. Goes away. Okay? All right, so now we need a rule. Because now we want to start finding it. Instead of talking about the theory, we want to actually start doing it. And it's not a matter of guess and check. We need to come up with a system that's going to allow me to find the antiderivative of that function. So the question is, what's the antiderivative of x cubed? If we can figure that out, we can hopefully come up with a process so that we can do it for any function that we get.
1/4 x to the 4th.
He said 1/4 x to the 4th. Is he right? Yeah. How do you know he's right?
Because when you take the derivative.
Perfect. Stop. Perfect. Okay. When you take the derivative of that, it makes sense that we're going to get back to x cubed. Plus c. That's going to happen a lot. Okay. A lot of times we're going to be doing stuff, and then somebody's going to shout out plus c. Usually it would be me. Don't forget your plus c. Okay. Does that make sense? Now, you want to tell me how you got that?
I added 1 to the exponent, and then had to figure out how that would make coefficient.
All right. Let's test your theory. Suppose I had x to the 5th.
So, x to the, or no, 1/6 x to the 6th.
Good.
We'll see.
Suppose I had x to the 2/3. Oh yeah. Now it got real. Good start. Am I writing here? Yes. Okay. So we did, what did I say? X to the 5th, and you did the antiderivative of x to the 5th. Okay, notice my notation. Antiderivative of x to the 5th, dx, because we're working with respect to x. And you said that was 1/6 x to the 6th. So then I gave you x to the 2/3. And you said it was what now?
3/5 x to the 5/3.
Is that right?
Yeah.
Plus c.
Okay, how'd you do that? That's a hard question, but if you can answer that question, then we're done. Then we have our basic rule, and we can do it for any polynomial, right? You want to help, Kate?
Yeah.
Go ahead.
You add 1 to the exponent,
I like that so far. Good.
and then you do whatever that number is, you do 1 over that.
Also known as a
Fraction. Reciprocal.
reciprocal. Okay, so let's. Everybody with you? With ya? All right, everybody with yourself? Yes. Let's try x to the nth. Feel free to jump in at any point. Go, Jimmy.
X to the, or I'm sorry, 1 over n x to the n plus 1.
I'm sorry, say that again.
1 over n
Plus
x
1. Plus 1.
plus.
There's some dissension
Oh,
in the
yeah,
ranks.
yeah. And 1 over n plus 1 x to the n plus 1.
Whoops.
Plus C.
Plus c.
Plus c.
Why is it 1 over n plus 1?
I don't know. Ask Jimmy.
Not just 1 over n.
Jimmy, why is it n plus 1?
Is it because you take the reciprocal of what you've added to the power?
Hold on. Well done.
I'm real proud of you. Go on, Jimmy.
It would be nice if it stayed that simple. It will for a while, because all we're going to do is take antiderivatives of polynomials and just do it over and over again. Okay? So x to the whatever we can handle now. What if there's a number out in front? What if I wanted to take the antiderivative of 2 times x to the 5th? Say again? What if you stick a constant out in front of it? So what's the antiderivative of 2x to the 5th?
Third x to the 6.
Good. Yeah. You treat it just like derivatives. The 2 doesn't matter. It just sits out in front. You do your thing with the x to the 5th, then you multiply the 2 back in. So the antiderivative of x to the 5th was 1/6 x to the 6th. There was a 2 out in front. You multiply it by the 1/6, you get 1/3. We got some practice for that. Good. By the way, this is really important. That's why it's flashing. It's the first of many flashes. Was that the breaking point for you? Another flashy thing. You should be happy about this.
Well,
Right?
I mean, there's other stuff.
There's always other stuff.
Gotta do more work.
There's no product rule, there's no quotient rule, and there's no chain rule.
Yes.
But
For
what is
integral.
there in
Why is there gonna be a but at the
there
end?
has
What's
to be
that?
something else?
No, there isn't.
Is there a
Well, there is. There's
There's
one.
always
There's one other
something.
thing which isn't that bad. But the reason this is really important is that some of you, many of you, all of you, at some point are going to try to do one of these things with an integral, and it doesn't work. So we have to figure out other ways to handle scenarios that would normally be a product rule, a chain rule, or a quotient rule. We'll get there eventually. Okay. It's not that bad. Nah, not really. It's okay. I mean, there's 3 things that you don't have to worry about for integrals. That should make you somewhat happy. Plus, it's in a flashy thing, so you know how important it is. Okay, so let's talk about some trig stuff. Here are 6 weird trig things. The top 2 are the most important, and the reason this is kind of weird is because it seems really contrived. So notice, if I'm going through a problem and I just happen to have to take the antiderivative of secant squared, because you know that pops up every once in a while, I can do that. Or if I need to take the antiderivative of secant tangent. So you get these bizarre things, and where do these bizarre things come from? Well, you have to remember, look at the right-hand side. These are all the trig functions that we took derivatives of, correct? And when you take the derivative of secant, you get secant tangent. So if I take the antiderivative of secant tangent, I'll get back to secant. Eventually, we're going to have to address the issue of taking the antiderivative of something straight up like the cotangent. But we'll worry about that later. And now we need to talk about the stupid golf thing. I'm not really proud of the following, but it might help some of you. And if it helps you, great. If it doesn't, then just forget about it. It's not my best thing ever, but it is kind of a dumb thing. The problem you're going to run into, like you did when we did derivatives, is remembering which one gets the minus sign. And I'm talking just about these top 2. I always had trouble remembering, is the antiderivative of cosine sine or negative sine? Is the antiderivative of sine cosine or negative cosine? And so I had somebody show me this. And again, I'm not proud of it, but if it works for you, fine. So here's how I always remember which one gets the negative sign. If I'm taking the antiderivative of sine, you with me so far? I look at the little integral thing as a golf club. That's a golf club. Go with it. And I look at the dot on the sign as being the golf ball. And so when I use the antiderivative symbol to smack that golf ball, it's going to travel very fast, right? Golf balls travel fast when they're struck. In fact, it travels so fast, it just kind of becomes a blur. Again, I'm not proud of it, but if it helps a couple of you. I thought about just getting rid of it, But again, I've had a couple people say, the golf thing is so stupid it works. So there's no golf ball in the cosine, so you can't get a minus sign on it.
Oh, yeah.
What's that?
What's the L is the golf ball?
You can't. It's in between a C and an X. How you gonna hit that out of, or C and an S? How you gonna hit it out of there?
Oh, well, you're never always.
You gotta hit down the ball.
You gotta hit down.
You gotta
You gotta
let you spin. You gotta put some more
Let's
effort.
say you're in the trees. Just grab a 1 iron and strike.
Just like in that
All right. Good luck then.
Thanks.
Try to help people, and they just rain on your parade. All right. Smarty pants. Find the antiderivative of 8x cubed plus 7. This is not a snack now. You'll get some of those later, but not this. This should be pretty straightforward. I mean, I'm just saying, you might want to use the golfy thing in this one, but you don't have to. If you find it stupid, then you mock it. Or you try to break it down. Is that everything? Oh, great question. I'll come back to that in a second. Alex, what'd you get?
2x fourth minus 7 cosine x plus c.
Plus C? Not 2C. Why would you say 2C? Technically, yes. However, Oliver.
I argue that it doesn't matter because C is constant anyways. So.
Right, one of the weird things you have to get used to is what's C plus C?
C.
C. What's C times C? What's C squared? What's the square root of C? What's C divided by C? C. Yeah. So no matter what you do.
Oh.
So yes. When you,
You said 1.
I said 1, so I.
I know, but it's still C.
Yeah.
You want to fight about it?
No, I got it.
Sure.
Fight.
I just did self-defense.
She did self-defense.
You go.
Can I use the hammer?
Yeah.
And then you got shit.
It was so funny. Wait,
I hate that. You guys, she was on. Okay, she like walled the guy. I think she
Because you don't know.
yeah. She was like, going, like it was scary.
There you go. Okay, so first of all, getting my notation correctly. Getting my notation correctly? That was horrible English. Getting my notation correct, I took the antiderivative of, and I put it in parentheses, because that's what you do. Constant of integration is in there. What variable am I using? Well, this is kind of obvious that the variable is x, but just keeping things above board. Most of you probably did this without splitting it up like I did, but I wanted to show you the true way to do it. Split it up into two different things, because the integral of a sum is the sum of the integrals. That 8 is not affecting anything, so I just stuck it out in front. The 7 is not mattering, so I stuck it out in front. Took the antiderivative of x to the third using the rules that Kate and Patrick came up with. 2x to the fourth minus 7 cosine x, and I stuck a plus c on the end of that, which you could argue was a 2c, but 2c is the same thing as c. Talking smack again. Question?
Do we have to show that word?
No.
Like,
And especially in a problem like this, you could probably just do that in your head. It's pretty simple. It's going to get a little bit nastier, but for the most part, that's pretty straightforward. Okay. Don't forget C term. Okay. Original integral. Rewrite it. How would you rewrite this? 5x to the 1/3 plus x to the negative fifth. Integrate it. Oh. Well, we did a fractional exponent already, but you did 2/3, right? Yeah, here's a 1/3. Shouldn't be a problem. What about a negative exponent?
Still a
Want to hear the most common mistake that people make in integrals? Across the board. Right. What's x to the negative fifth? What's the integral of x to the negative fifth?
X to negative 4.
Negative
Negative
4.
Oh, no, sorry.
It is -4, not -6.
Oh,
Okay. Yeah, people have trouble adding 1 to a negative number. Oh, that was a big jump. I thought I had the answer in there. Antiderivative of 12x to the fourth?
12 fifths x to
12 fifths x to
the fifth.
the fifth. Antiderivative of -5x to the 1/3? 4/3, 3/5. 15 fourths x to the 4/3? And we talked about that one already. Okay, it's a negative exponent, so adding 1 to it would make it -1/4, so -1/4 x to the -4.
Wait, can you say all that again?
Certainly.
The anti-derivative.
12 fifths x to the fifth. Good. Minus 15 fourths x to the 4/3 minus 1/4 x to the -4. Nothing to simplify there, so you're done. Oops, what did I forget? Plus C, very good. Okay. We're going to stop there. So the plan is Monday and Tuesday, there's a little bit more in this slideshow. I'll have some homework for you to go over and stuff like that. There's a little bit more to finish in the slideshow about some basic integration stuff. And then Tuesday is pretty much going to be